Okay, we are starting. All right, so this is actually the last lecture on systems of nonlinear equations, and then we'll be looking at this topic on Wednesday in the lab. Okay, so we'll do one more method, avoidance method. So Morrison's method is a modification of Newton's method. So if we just look at the main step of Newton's method, the vector that has to be added to xk to get xk plus 1 is minus the Jacobian of f evaluated at xk inverse times f evaluated at xk. Now, do not explicitly compute the inverse, as I mentioned last time. Okay. Am I still recording? Yes. Okay. But even without doing that, because you would carry this out by Gaussian elimination and forward back substitution, but regardless of how you carry this out, this is order n cubed floating point operations per iteration. So especially if you're solving a large system of equations, this is a very expensive step, and it would be nice to try to cut that down. So this is just too slow. So we want to try to get around that if we can. All right. Now, the idea behind our fix, if you will, for Newton's method, Avoidance method, is well, actually, I can discuss more than one fix. Because not only do we have to solve the system of equations, this Jacobian requires computing partial derivatives of f. And these partial derivatives must be evaluated every single iteration. So we have two bad things happening: computing derivatives and then solving a system of linear equations involving those derivatives. Okay.
Derivative fix can be done with secant method.
That's the first thing we're going to talk about. So the first thing is secant method. And that uses approximate derivatives instead of analytical derivatives. Okay, so that at least deals with this problem. Because, I should say, but, you still have to solve a system of form ax equals b with each iteration. In other words, this problem right here, secant method does not help at all with addressing that. So we need a different approach, and that's why I'm not really going to talk about secant method today. And secant method, it's the same as Newton's method, except you're replacing this exact Jacobian with an approximate Jacobian. So you're having to evaluate f at your new iterate anyway, so you can do like f of xk over f of xk minus 1 divided by changes in each of your variables. So it's easy enough to compute, but once you have your approximate Jacobian, you still have to do the inversion. Okay, so we want to get around having to do a new inversion every single iteration. So our focus today, avoidance method. Okay, is all right. So it eliminates most of the inversions. And it uses the fact that as this iteration proceeds, presumably xk is converging some x star. So the Jacobians should be converging too. So what that means is, if your matrices from iteration to iteration, your Jacobian matrices are all different. Therefore, you have to solve a system from scratch. You have to do a new LU decomposition from scratch, forward-back substitution. You can't reuse any of that information from one iteration to the next. But because these Jacobians are converging to one another, you might think, oh, well, as they converge, maybe we can reuse some information. Because at least whatever LU decomposition you got from your last iteration, you should be able to approximately reuse it in some form for the next iteration. But we don't have any obvious way to do that. Just because these Jacobians are converging, because they're not exactly equal, it's not clear how we can take advantage of that. So the model that Avoidance method uses so the key assumption for Avoidance method is that the Jacobian of f at xk plus 1, bless you, can be well approximated by the Jacobian at f plus an expression of this form, plus some matrix of the form uv transpose, where u and v are both column vectors. This is called an outer product update. Okay, so the idea is Avoidance method will start, first iteration, with the true Jacobian. So the first iteration, it's going to take it on the chin and just go ahead and go through all the expense of Newton's method of a first iteration. But from that point on, as we go from iteration to iteration, it's going to not recompute the full Jacobian, and certainly not invert it, but it's just going to do a cheap update to the previous Jacobian to get the next Jacobian. And since the Jacobians are all converging to one another anyway, then this will converge to the kind of behavior you'd expect from Newton's method. And the reason why we're making this assumption is when you have a matrix that's changed only by an outer product update, then if you know the inverse of this matrix, you can get the inverse of this one. So outer product updates are easy to invert. Now, you're going to find this statement of mine rather curious by the time this class is over, because I'm going to show you how you can invert an outer product update in terms of the inverse of your original matrix. And I can assure you that deriving all that is not easy. But once we have a final result, then it's easy to use.
Where is U and V coming from?
But I'll show you. Yeah, so the point is right now we just have some vector U and V. We need to pick the right ones. Yeah. Okay. So I'm going to first discuss a more abstract problem. If you have some matrix you know how to invert, and you perform an outer product update, how do you compute the new inverse, and then we'll apply that to this Jacobian from Newton's method and obtain Avoidance method. Let's see if I can do this without somehow stopping the recording. Okay, so now it's time to put your linear algebra hats on, if you have them. Okay, so given a matrix of this form, B is equal to A plus an outer product update, UV transpose. So A, U, and V are all given. All right, so then B is of this form. How to get B inverse in terms of A inverse? And what that, oh dang it, that's the only good piece of chalk I had. And it's broken.
Right. Yeah, I got some.
Okay. Thank you. So, yeah, 'cause I have chalk up here is all tiny little knobs. Oh, okay. Your lightsaber. Okay. How do we get B inverse from A inverse? Because that way, if you are able to solve AX equals B, where that's a little b, you can solve BX equals little b also. All right. Now, so I mentioned this outer product update. It has another name. It's also called a rank 1 update. Because actually this is the first homework problem in Nat 610, which I'm offering next spring, numerical linear algebra. One of the first homework problems I give is to prove that a matrix C has rank 1 if and only if C has this form, U is equal to UV transpose for some vectors U and V. And by rank, what we were just talking about rank before class, rank is a number of linearly independent rows that the matrix has, which is also equal to the number of linearly independent columns. Rank 1 matrices are nice because the multiplication is very simple to carry out. Cij is just Ui Bj. So, whereas normal matrix multiplication is a pain, because for each entry you have to compute a summation, but not in a rank 1 case. And there are a lot of conveniences about rank 1 updates that we'll take advantage of here.
So just writing that UI, VJ shows that they're both linearly independent?
Well, I'm just saying here's what this product looks like. But yeah, how you would prove this actually does turn out to rely on this information. Because what's going to happen is, for instance, if I look at what C is in general, we have U1, V1, U1, V2, V3, and so forth. And then U2, V1, U2, V2, U2, V3. So in other words, the first column is V1 times U. The second column is V2 times U. All the columns are multiples of each other. Are multiples of U. Every row is a multiple of V transpose. So I kind of give away the answer to that problem, but
That's okay.
so if you hold on to that information for a year, but okay. But that's the idea. That's why it's rank 1. All the rows or all the columns are scalar multiples of one another. Okay. Now, okay. So how do we get B inverse in terms of A inverse? So first observation we make is, suppose we have this equation, AX is equal to U, where this U is the same as this U up here. Okay. Well, in that case, Bx is A plus UV transpose X. And if I multiply this out, I have AX plus U V transpose X. And now I'm about to show you why we like outer product or rank 1 updates, why they're so convenient. Because this expression here, V transpose X, that's a dot product. It's just a number. So you can move it around. Because AX is equal to U, so in other words, this becomes, so this is U, and this is a multiple of U. So I can express it that way. So this is a dot product, U dot V. No, it's not U dot V. V dot X. Okay. All right. So now Bx is equal to this number, 1 plus V transpose X is just a scalar, times U. So I can rearrange this and say that V inverse U is equal to 1 over this number, 1 plus V transpose X, times times X, but X is A inverse U. Okay. So in other words, I now know something about B inverse. So in other words, by knowing how A inverse acts on the vector U, I know how B inverse acts on the vector U. Now, the thing is, that's only giving me a little bit of information about what B inverse does. Because assuming all these matrices are n by n, A and B are linear operators on an n-dimensional space. If I want to know all about B or B inverse, I need to know how it acts on all n dimensions. I've only covered one dimension here, U. So I need to know what else B inverse does. Fortunately, because again it's a rank 1 update, that information is easier to get than it normally would be. Okay. Now, so now let's let X satisfy this condition, that V transpose A inverse X is 0. Now, another way of writing this is that A inverse transpose V transpose X is 0. In other words, x is orthogonal to this vector, A inverse transpose V. But the thing is, given any vector, there's an n minus 1 dimensional subspace of Rn that is orthogonal to it. So in other words, I've described most of Rn except for one dimension. Okay. Now, if I look at V A inverse x, okay. Well, B is A plus U V transpose, A inverse times x. So now I'm going to multiply all this out. So I'm going to get A inverse x plus U V transpose A inverse x. But this right here is 0. And what is this?
Identity.
Yeah, A inverse is identity, so all this is just x. So in the end, that's what we get. So B A inverse x equals x. But now I can move B to the other side. And I get A inverse x equals B inverse x. In other words, A inverse and B inverse are exactly the same on most of the vector space, on n minus 1 dimensions out of n. It's only this case over here that I did earlier where they disagree. And that's why rank 1 updates are nice. That a rank 1 update doesn't really change the matrix or the transformation all that much. It only affects it along one direction. Okay. So now I'm going to abstract this problem a little further in light of what we've seen here. So suppose I'm given a matrix C. Find a matrix D such that the following holds. First property is that dW is equal to Z for given specific vectors or fixed vectors W and Z. So in other words, along a particular direction, W, I want D to perform this action, to map it to Z. Okay. The other property is dy is equal to cy if y is orthogonal to a given vector G. Now, I'm going to explain how this abstract problem relates to the semi-abstract problem I was just talking about. Because obviously we're a long way from Newton's method right now, but we'll get back to it before class is over, I promise. Okay. Actually, yeah. I only have one page of notes left after this. Now, I'm going to do some notation mapping here. So C over here corresponds to A inverse. D corresponds to the matrix I'm looking for, B inverse. W corresponds to vector U in the outer product update. Z is equal to 1 over 1 plus V transpose A inverse U times A inverse U. You can see why I adopted this notation, because I don't want to have to work with this expression a bazillion times. Okay. And finally, G is A inverse transpose times V. Okay. All right. Now, so it turns out this problem I can write down a solution to. Matrix D is a matrix C plus Z minus CW G transpose over G transpose W. Okay. So this is the unique matrix that has both of these properties. And you can confirm that by actually carrying out these multiplications in properties 1 and 2. I said some uncertainty.
So you got that from your two identities right there, not from
Oh yeah, I got these from
that.
that and that.
Okay.
Yeah, they're exactly the same except drastically simplified notation.
Right.
Okay. Because now that I've solved this problem with simpler notation, I can apply that to over there. Okay, but let's first, I want you guys to be convinced that this is a matrix that works. So, if I look at dW, so what do I get? I get CW plus Z minus CW G transpose W over G transpose W. Well, these dot products cancel out. So what's left is CW plus Z minus CW. So the CW's cancel out also, and you get Z. And then dy is C plus CY plus Z minus CW G transpose Y over G transpose W. But if Y is orthogonal to G, that part is 0. So that wipes out this entire term. And all that's left is CY. So now you can see that this matrix is, this is a rank 1 update too. This is a vector times a vector transpose. That's just a scalar. So now we have a way to express B inverse as an outer product update of A inverse. So any questions up to this point before we start unwinding all of this? Okay. So now I can write down a formula, a very ugly one at that, for B inverse. And then I can make it into something somewhat less ugly. Dang it. That's why it's good to have a case. Okay. Okay. Now, okay. So now if I take okay. So now if I unwind all notation, D is B inverse, C is A inverse, and then Z is a mess. 1 plus B transpose A inverse U times A inverse U. CW is A inverse U. And then G transpose is B transpose A inverse. all over G transpose W, which is V transpose A inverse U. All right. Okay. Now, let's clean this up a little bit. For one thing, it's possible to, we can certainly factor out an A inverse U over here. So then I have 1 over 1 plus V transpose A inverse U minus 1 A inverse U V transpose A inverse all over V transpose A inverse U. And now we can put this over a common denominator, and that's going to simplify to, okay, so I'm going to have my common denominator is 1, it's just going to be this. So I'm going to have 1 minus all that. And the numerator up here is going to be just this with a minus. So we're going to cancel out. So we're going to get a minus A inverse U V transpose A inverse over 1 plus V transpose A inverse U. So this is the simplest we can get this formula. So this is called the Sherman Morrison formula. Okay.
Take out to give you a negative.
Yeah, because when I put this over a common denominator, I'm going to get 1 minus 1 minus that.
All that, yeah.
So the minus, so that goes here.
You're right.
The numerator cancels with the denominator,
Okay, yeah.
and then the denominator stays.
Right.
Okay. Now, this is for a case where we have a rank 1 update. If A is modified by a rank K update to produce B, it turns out that B inverse is a rank K update of A inverse. So the more general form of this, it's called a Sherman-Morrison-Woodbury formula. Now, I don't know if all three of them work together, or if Woodbury came along and said, hey, I'll make this better. Who knows? But and we don't need that for our purposes, so I'm not going to go into that. But that formula exists. Sherman-Morrison-Woodbury formula is more general. Okay. Where instead of dividing by number, this number becomes a K by K matrix, but that has to be inverted, so it gets uglier still. Okay. Now, how are we going to modify Newton's method using this formula? Okay. So, to come up with Avoidance method, I'm finally coming back to the original thing. Okay. So, during our first iteration, I'll let A0 be the true Jacobian. So, Jacobian at your initial guess, x0. What we'll do next is we find A1 that is an approximation of a true Jacobian at x1. Such that, first of all, A1 times x1 minus x naught equals f of x1 minus f of x naught. Now this seems like a very strange relationship, but the idea is change in f equals change in x times derivative. because A1 is meant to approximate the derivative. So you can think of this as being a secant approximation, but only along one direction, x1 minus x naught. Okay. All right. So in other words, this comes from f prime of x1 from Newton's method in one dimension is approximated by f of x1 minus f of x naught over x1 minus x naught in a secant method in one dimension. So we just rearrange this because A1 plays a role of a derivative. Okay, so that's one property. So this corresponds to this. dw is equal to z. Okay. Now, the other property that we want this approximate Jacobian to have is that if z transpose times this difference in x's is 0, so if z is orthogonal to this direction, then A1z is just equal to A0z. So in other words, on all these n-1 directions, our new approximate Jacobian will just do the same thing as our old approximate Jacobian. Okay. All right. Now, this gives us a way to approximate. This gives us a formula for A1 because these two properties correspond to the two properties over there. Again, just changing notation. So that allows us to express A1 as an outer product update of A0. Okay. Now, what this means is A1 is equal to A0 plus, okay, I need to introduce some notation here. I'll let Y1 be f of x1. Oh, these should have vector signs on them. Okay. Minus f at x0. Okay. And then S1 is x1 minus x0. Okay. Now, based on the previous formula, like that I got used to get this d from c, I get y1 minus a0s times s1 transpose over S1 transpose S1. All right. Now, using a previous notation, A0 to C, A1 equals D. Y1 is Z. That's S1. S1 equals W. And equals G. So it plays both roles. Okay. All right. So now that I have A1 expressed as an outer product update of A0, I could use a Sherman-Morrison formula to express A1 inverse in terms of A0 inverse. So So A1 inverse is A0 inverse minus this monstrosity. Plus okay. Now this can be simplified somewhat. What am I doing on time? Okay. Okay. Because what happens here is, let's see. Oh, because if A0 inverse times A0 S1, so there's a cancellation here, that simplifies things a little bit, and we get plus S1 minus A0 inverse Y1 S1 transpose A0 inverse, and all of that is over S1 transpose A0 inverse Y1. Okay, so so now what we can do is we have S2 is, which S1 is the difference between x's. That's that vector we want to compute from each iteration to the next. Assuming we already have S1 from our prior iteration, now we can get our next vector S2, which is just minus A1 inverse f of x1. And this we now have because we just used the outer product update. And then we can say x2 is equal to x1 plus s2. And now our second iteration is computed. So the first iteration is just Newton's method, exactly, no change. Then we take our Jacobian from a previous iteration, update it to get the new Jacobian inverse, and now this part right here is not a matrix inversion, it's not Gaussian elimination. In the first iteration it is, but from this point on, all this is matrix vector multiplication, which takes on the order of n squared floating point operations rather than n cubed. In other words, we've cut out an order of magnitude from the expense of each iteration. So A0 inverse, we have to go through all the trouble to compute that. So there's no getting around that. The first iteration is still bad. But by continually doing these outer product updates from that point on, we can go ahead and incur much less expense in all those other iterations. Only n squared work for each one. So overall, we get some savings. So now what I can do is I'm going to write down the entire algorithm for avoidance method that just uses this idea at each iteration. So then you can see where the real expense is coming from. And also how this formula, as messy as it is, can be implemented as efficiently as possible. Okay. Okay. So first, we need initial guess, just like the use method. Okay. Then we compute the Jacobian from that initial guess. So still to carry out the true differentiation there. Then we carry out a Newton step. So minus A0 inverse the difference is, it's not enough to do just Gaussian elimination. Well, actually, yeah. Unfortunately, we need the whole inverse just for this first iteration, but so that's kind of a pain to get, but then we won't need any inverses after that. So now we compute x1 just by updating our initial guess. And then I'll set my iteration counter to 1. So this is just the same as Newton's first iteration, except if this were truly Newton's method, it could do this part more cheaply, not compute the whole inverse, just do Gaussian elimination and back substitution. So it's still almost as expensive. It's order n cubed operation, it's just somewhat less. Okay, now, because I'm running out of room, I'll do my loop over here. Okay. So first I compute my y vector, so this is difference of f values. And keep in mind my s vectors, you know, S1, S2, etc., those are difference of x values. Okay, now for a shorthand, for later, I'll compute this quantity wk, which is my previous inverse times my y value. Another convenience, just a constant. And now I can more concisely express my new inverse Jacobian. Okay. So my new inverse Jacobian is my previous inverse Jacobian plus this outer product update. In fact, if I go ahead and, this is a vector, if I go ahead and compute that up front, then the outer product update is easy to apply because outer products have such a simple structure to them. Each entry is just a single product of numbers. Okay. Now I can get my new S vector by applying this new inverse Jacobian to my latest F values. Okay. And then I can update my X. And then bump up my iteration count. And that's it. Of course, I can check for convergence somewhere in here, like using some sort of if statement. So as far as how much work is done here, so here, whatever cost there is in evaluating f, the Secant method will give you the same thing. Here we have a matrix vector multiplication. Here we just have dot product, so that's cheap. Here also we have a matrix vector multiplication. And then here too, we have a matrix vector multiplication. Everything else is cheaper than that. So we're trading solving the system linear equations using Gaussian elimination, so an order n cubed operation, with 3 operations that are order n squared each. So for a large system of equations, it definitely is worthwhile to go to trouble using Avoidance method. And what will happen is, as the iteration proceeds, the Jacobian will be off at first, but it will converge to effectively act like a true Jacobian, at least in the direction that it needs to. So it won't converge as rapidly as Newton's method, or Secant method for that matter, but considering how much cost saving there is per iteration, the overall cost is going to be less. So using the magic of outer product updates, a lot of savings can be realized at each iteration. But what is an ugly derivation?
So did we ever, in the beginning, in the key assumption, we said it was going to be the Jacobian evaluated x plus UV transpose?
Yeah.
We're talking about what UV transpose was the outer product update?
Yes.
And is that what that finds? Or does it find?
Well, yeah, so really, so what happens is, yeah, so the new Jacobian, a new approximate Jacobian is equal to the old approximate Jacobian plus, and so the actual outer product update is okay, so this is your U, and that is your V. It's from this formula here.
Okay.
Okay, yeah, I know it's made the notation more general. Okay.
But that came from rewriting.
Okay. This, you mean? Okay, that came from the conditions we imposed on the approximate Jacobian. That it acts like a secant in one direction and preserves the action of a previous Jacobian in all other directions. Which may not be the best idea because those partial derivatives change as the iteration proceeds. That's why it's still important to have a good initial guess. So at least the Jacobian will be off by that much.
That's your V transpose?
Oh, yeah. Okay. Yeah, so that's it. So, yes, SK over its inner product itself is V. Okay. Any other questions? No? Okay, well, we'll see code for this in the lab also for Newton's method and fixed point iteration. So be sure to be downstairs on Wednesday. Wow, finished up early.